I'm Panda. I'm going to be talking about data-driven connectivity. What that is will become clear soon. So networks right now have this division of concerns. Everyone kind of knows about it. We have routing in the control plane, and routing here just involves setting up paths. And it operates in the order of milliseconds and takes a while forwarding along these paths is done by the data plane, which only takes microseconds and is pretty fast. And this separation has served us well, except now we have new emerging classes of users. Like we have high-frequency trading firms like Knight that require low-latency access to the stock exchange, for instance. Or we have telephony applications happening over these networks where users require high reliability. And in these cases, having the control plane deal with link failures is actually pretty expensive because you have to wait for convergence, and that could be forever. And ISPs today deal with this using pre-computed backup paths. So for instance, they'd use MPLS fast readout to do this. And one of the problems with backup paths is typically current solutions support a single link failure. And if you wanted to expand to supporting a larger number of links, state required grows exponentially. So it's actually pretty expensive to set things up for this. And what that means is that it's actually pretty hard to generalize this sort of an approach. But it's also hard to configure because a separate problem with backup paths is that link failures aren't independent. Links happen to pass through the same tunnel or be in the same geographic area, might be more likely to be cut. And so you need to account for these sorts of correlations in failures. And people get this wrong all the time. And we've seen like a bunch of ASs go down because of problems like this. So what we actually are trying to argue in this work is that part of the problem here is that routing is conflating these two functions. The first is optimality, which says use good paths. And good here might be use shortest paths or use paths which have the most capacity or something else. And optimality conditions are often global. You need some amount of coordination just to figure out that a particular path is shortest. You can't compute this locally. Well, the second feature is a function that that is being served by routing is connectivity, which is just get my packets to the destination. I don't care what path you take as long as they get there. And what we claim is that connectivity can actually be done locally. And so the way we want to use the fact that connectivity can be done locally is we want to push connectivity to the data plane. So essentially, when link failures happen, we want packets to be forwarded to the destination really quickly, regardless of how long control plane convergence takes. And so that's great. We want to push connectivity to the data plane, but it's unclear what pushing something to the data plane really means. And so a common set of assumptions that people make about data plane algorithms is they don't make FIB changes. Writing to the FIB is commonly done by the control plane. It takes a while. You probably don't want additional data in your packet header. Unfortunately, it's impossible. We have a result in PodC last year which shows that with these particular constraints, we're not getting to the kind of connectivity we want. But I'm still talking here, so we're not going to be constrained by this. And so what we do is when you are faced with an impossibility, we try and relax a constraint. And so it turns out that in reality, switches already have features that require rewriting the FIB based on data plane events. There is at least one major switch manufacturer which has talked to us about the fact that their ASICs do these sorts of rewrites. And as long as you only rewrite a few bits in the FIB, not the entire FIB, it's actually doable. So given that we can write a few bits in the FIB, and we'll get to exactly how many bits shortly, is that enough? Can we get connectivity with that? And so here, for the rest of this talk, I'm going to present a method to use these few bits to get connectivity. And we're going to go through this three-step process to actually arrive at this result. So the first one is we're going to start taking advantage of redundancy that's already available in networks that is kind of being wasted and not being used. After that, we'll actually find a data plane mechanism that can restore connectivity. And once we're done with that, we'll go back to worrying about optimality and how the control plane interacts with our mechanism. So let's start from the top. What do I mean by there's already redundancy available? So if you take any current control plane routing algorithm, for instance, OSPF, just for simplicity, you're calculating paths that meet certain optimality criteria, in this case, shortest paths. And there's all these grayed out links that are just lying around in the network that can lead to a particular destination, but aren't being used because maybe they aren't the shortest paths. So what we want to do is we want to extend the routing table and the paths to take advantage of these links. And so the way we do this is a very simple extension. If you have a link, have it go from a node that is farther away to a node that is closer. And when there's some sort of tie, just break the tie deterministically, maybe based on node IDs. And what this should lead to is a DAG, which uses all the links and can get the packet to the destination. So this already increases the amount of the reliability of the network somewhat, since cutting down certain links no longer means you need to recompute anything. So now that we've done this, the next question is how do we restore connectivity when connectivity is in fact lost, even with this redundancy? So for instance, in the network that's shown right now, a single link failure can actually result in disconnection. So in this particular case, the orange node has no paths to the destination. And so we kind of want to recreate a path for it, and what we do is we reverse all the links connecting the orange node to the network. So both links that used to point inwards now point outwards. And there's a proof that was written out by Gaffney and Bitsakis in '81 that shows that a finite series of such reversals will reconnect the DAG. It will result in a destination-oriented DAG. So now we have this algorithm, however, and it can restore connectivity, but it's synchronous. So if you remember, when the links flipped, the entire graph agreed that the links had changed direction. And the problem is the data plane as it exists right now is not synchronous, it's asynchronous. And in particular, there are two problems that any data plane implementation of this algorithm must address. The first one is notifications. That is, when a node decides that it wants to reverse a link and sends a control packet saying, hey, my link has been reversed, these notifications can be lost. And we need to make sure that everyone on the network somehow remains on the same page, even if many of these notifications end up getting lost. The second one is these notifications can be delayed. You could have two packets cross each other, one of them notifying that a link has changed direction, or something else might happen. So we solve these problems, and the exact details of the algorithm and how we solve it are enumerated in the paper, but instead of going through the algorithm in great detail, I'm going to go through a short walkthrough that gives a flavor for how the algorithm solves these problems. So for my walkthrough, I'm going to be using this sub-part of a graph. There are other nodes around. We just don't care about them. We will only focus on these two nodes for now. And essentially, there's a link failure, and the blue node has now lost its only output link. It doesn't have a place to send packets. But it happens to have a packet that really needs to get to the destination somehow. So the first thing we want to do is we want to somehow create a link that points outward. Before we do that, I'm going to annotate this node with some additional information. So, OK. So remember, I said previously, one of the problems we need to solve is that notifications can be delayed. And so to deal with delayed notifications, one of the things we do is we use versioning. We use a sequence number that versions the direction of the link at a particular node. And in this case, this is noted in the local sequence number. We use a separate version number, the remote sequence number, to track the version of the link direction version for the node on the other side. And for performance reasons, we do a partial reversal, which means that we keep a set of links that we want to reverse at any given time. So again, to back up, we originally, before any of this annotation, we really just wanted to reverse a link, and we were just going through how one would do that. So to reverse a link, it's pretty simple. The node just reverses the link. It sets the direction to point the other ways. It increments the local sequence number as a way of indicating that the version of its link direction information has changed. And then it forwards the packet, and the packet carries with it the sequence number, and hence every packet arrival can act as a notification. So if a packet arrives going the wrong way, you know that the link might have changed direction, and because there's a sequence number inside the packet, you know what the version of the information at that node is. So having done that, let's look at what happens on the other side with the pink node, which is now going to receive this packet. So the pink node receives a packet going the wrong way, and this is potentially a notification that link direction has changed. So the first thing it's going to do is compare sequence numbers as a way to check if the version of information held by the blue node has actually changed. And it finds that, well, you know, the numbers are different, so something changed. It reverses the link, and it's done. So to back up and look at this from a higher level, at some point, the blue node wanted to reverse a link, which, as we've already discussed in an earlier slide, can lead to a connected DAG. And so what it does is it sent a packet with an updated sequence number as a sign that the link should be reversed. The pink node received this. It agreed that something had changed. It reversed the link. And now we've reversed the link for the entire graph. OK, so to go back to our original aim, we started with wanting to restore connectivity. We did this entire thing of routing on a DAG, so we got additional resilience, and we have this nice algorithm that can restore connectivity. The problem, though, is the paths produced by this algorithm aren't necessarily optimal. In fact, we say nothing about what optimality so far. So what we use to restore optimalities, we allow a control plane algorithm to run. And what we show in the paper is that any control plane algorithm that can produce a DAG can run. So most control plane algorithms that are common should work fine. But we need the control plane to not interfere with the data plane. In particular, the control plane might want to influence paths at the same time as links are failing, and the data plane is trying to maintain connectivity. Having these two race against each other would not be very good. So to solve this, we build a safe primitive, and a safe here just means it prevents races of this sort. And the primitive we build sets all edges of a node to point outwards. So it just makes all links in a node outwards. The details of how the primitive is built and how it can be used are described in greater detail in the paper. OK, so far, hopefully, we've described this method to maintain connectivity, which started with making use of all of the redundancy available, this algorithm that can restore connectivity, and we have some data plane stuff, or we have some control plane stuff. But maybe you're curious about how it works in real life. So the paper has a large set of micro and macro benchmarks. But here we're going to focus on a macro benchmark which just shows what is the advantage of using DDC in networks which already have a lot of redundancy, for instance, data center networks. And the second one is, remember a long time ago I said we're making FIB updates at packet rates, but I didn't really say what packet rates really meant. Did it mean line rate or not? And so we're going to look at what happens as FIB update rates vary. So we start with kind of the part where is DDC useful in networks which have high resilience, which already are pretty resilient. So we use an 8-pod fat tree, and this is a pretty common data center topology, and we use a partition aggregate workload, which is common for interactive for front-end facing data centers. And we simulate 5 link failures for 550 seconds. So during these 550 seconds, there is no control plane convergence, but there is, we are using ECMP. So for instance, in cases where multiple paths are available, you can in fact take multiple paths. And we look at the percentage of requests that are fulfilled, bucketed into 10-second intervals. And in a result that is somewhat similar to what the F10 result will show in a couple of days, actually, even despite all of this available redundancy, actually, during certain failures can affect fat trees pretty poorly, and at the worst, we see something like only 86% of requests even reaching the server that has to respond to them. So the other thing that is a problem for data centers, or is a concern for data center operators, is latency. There's this common saying, if they'd rather have no requests show up than have requests show up late. So we also looked at what the latency was. And so the blue line without DDC has all of the requests for which we saw no responses set to infinite time. And what we find is that at worst, DDC, the tail with DDC is about 2x as bad as the median. Or actually, it's less than 2x as bad as the median. So, okay, now to answer the second question of what happens if you can't update your FIB quite as fast as a single packet arrival. So far, I've assumed that FIB updates are happening at packet rates. So this is, for these results, we look at what happens if they're bad. And so we start by looking at what happens on packet latency, and this is a micro benchmark, so we make sure all of the packets are affected and all packets result in actual reversal. So this is before the data plane converges, this is before the control plane kicks in, this is before any of that stuff happens. And so the black line here is the results with what we've seen so far, which is if your FIB updates are instantaneous. The blue line shows what happens if FIB updates take a millisecond, which is sort of a really bad number because at that point, you might be, like current existing mechanisms can already write to the FIB at that rate. And even with a 1 millisecond update time, what we find is 99% of packets have a latency of under 3 milliseconds. None of the packets get dropped, but there's a pretty long tail in the latency. And the reason for the long tail is in some particularly bad cases, with FIB update delays, a packet might end up bouncing between a couple of switches for a bit until a FIB write actually happens and it's sent along another path. So the other question one might ask with FIB update delays is what happens to TCP throughput. So for this, we used a WAN topology and 1 Gbps links for ease of simulation. And again, we find that statistically, there isn't any difference between the two. So there's a bunch of work similar to this that's already been done. There's FCP from SIGCOMM 2007, which has a problem that it has unbounded header bits and might require the FIB to change completely. There's also packet recycling, which was in hotnets 2 years ago, or 3 years ago. It's actually pretty promising, except DDC is significantly simpler. It doesn't require you to solve this graph genealogy problem. F10, which you'll hear about tomorrow, is a slightly more specific version of DDC. It only works under a very specific set of failure circumstances and doesn't provide any guarantees as a result, but it uses a similar mechanism of flipping the link around and sending it back. Okay, finally, this is my last slide. So let's say ASICs did implement DDC. What happens, or how does that change the world? So there's clearly a lot of interest in having connectivity being maintained. So by doing this, suddenly connectivity becomes a data plane concern, and a lot of control plane applications can now worry about providing other kinds of services and not rely on connectivity. The other thing is, control plane applications are currently have this two-stage thing where they first need to go establish connectivity on the network they use for coordination. If you push connectivity down to the data plane, they can actually rely on on a richer set of coordination. And that's it. I'll take questions.
Hi, Omar Javed from the University of Washington. I have a couple of questions. The first is this concept of DAGs. So if a node is storing multiple links, is that really different from storing multiple paths towards that destination? Like instead of having one link that you'll need to, that you forward packets on, you store multiple links, right?
Yes.
Is that the same as storing multiple paths?
No, because you can imagine that multiple paths could be multiple. So it's more restrictive than multiple paths. With multiple paths, you can imagine that if a packet comes in from A, node B sends it to C, while if a packet comes in from, say, node D, it sends it to E. So paths is kind of at the point. So in a DAG, when you get to a particular node, your next hop is determined entirely by the destination. It's not determined by anything else, which is different from a path, where it's determined both by where you're coming in from and the destination.
So in this case, you're absolutely sure that all the links that you store as towards the next hop for a particular destination, all those links will turn into an eventual end-to-end path that will lead to that destination.
Yes. So part of the thing with DDC is it guarantees that when a packet gets to any node, it can find a path to the destination from that node. So yes, absolutely.
Cool. Second question is that I had difficulty grasping this idea of reversing links.
Okay.
So this kind of thing possibly could not work on a topology like the wider internet, where you have business agreements between different ISPs. So if you have a link between customer to provider, you can reverse that.
So I apologize, I didn't specify this more clearly. This mechanism is only for inter-domain routing, it's for intra-domain routing, not for inter-domain routing. So it's within a single administrative domain.
Okay. So perhaps you could shed some light on dealing with failures in the inter-domain case. So is there any hope that this kind of architecture would work in that domain? So
it depends on, as you said, a lot of it depends on business relationships. With current BGP, I don't think so. I don't know. I could imagine someone extending BGP in a way that it allows such a mechanism to work.
All right, cool. Thank you.
No problem.
Hi, Mike Fried in Princeton. I might have missed one bit in the talk in that at the beginning you were talking about how some of the current firmware, some vendors supported a certain number of bits. I somewhat later expected you to say, kind of characterize that we need 3 bits is enough or something, and maybe I missed that one part.
Okay, so so I didn't say it in the talk, it's mentioned in the paper, but for us we basically need either 3 bits or the use of virtual tunnels.
Okay, so I guess my follow-on question was, so this is one thing where you look at what the vendors currently support, you say they support X bits, we could do it with 3 bits. Possibly they didn't try to design more than that because nobody was using it. So I guess, speaking not as an architecture person, is there a hard limit? Is this throwing a couple extra wires in there? Is, architecture people 5 years from now, we could do 50 bits if there's use for it?
So I will be very honest. I know nothing about ASIC design. I've never done engineering.
Let me ask a different question. If you had 20 bits or 50 bits, would that make your problem different, easier?
I don't. So actually, I think the current algorithm we have is pretty easy. It's pretty simple. I don't think it changes the current algorithm. There might be ways it makes the backup, the path that you get during failures more resilient, more optimal at times, but I'm not entirely sure. Sorry.
Okay, thank you.